what if the absolute best way to manage crazy complex problems isn't to add more features, but to actually take some away? Today, we're diving into one of the most important papers in all of computer science history, C.A.R. Hoare's 1978 masterpiece, Communicating Sequential Processes.
So picture this. It's 1978. This paper drops in the Communications of the ACM, and it's not just some dry academic theory. Oh no, it was a totally radical proposal, a whole new philosophy for how we should think about and write programs that need to do many things at once. And it was a direct answer to a huge crisis that was brewing in the world of software.
To really get why this paper was such a game changer, we got to hop into Time Machine for a second and understand the programming nightmare it was trying to fix.
See, back in the day, the only real way for different parts of a program to work together was for them all to read and write from the same shared block of memory. I mean, just imagine a bunch of people trying to edit the same Word doc at the same time without tracking changes. As the paper itself says, this created severe problems. It was a total recipe for chaos.
Think about that whiteboard analogy for a second. If you have 5 people all trying to scribble on it at once, you'd need this complicated mess of rules, locks, semaphores, basically traffic cops, just to stop them from writing over each other and making it unreadable. Hoare's big idea was, what if we just get rid of the whiteboard entirely? Instead, what if everyone just sends each other sealed private letters?
And that radically simple idea is called Communicating Sequential Processes, or, CSP for short.
In the world of CSP, every single process is its own little isolated island. It has its own private memory, and it absolutely cannot see or touch the memory of any other process. The only way they can coordinate, the only way they know what the others are doing, is by explicitly sending and receiving messages.
You have to understand, before this paper, input and output were kind of just an afterthought, something you bolted onto a language at the end. Hoare came along and said, no, that's all wrong. He argued that sending and receiving information should be the absolute bedrock, the central organizing principle of any concurrent system.
Okay, so that's the big picture. But how does this communication actually work? Like, what does it look like when you're writing the code?
Well, this is the beautiful part. It is so simple. CSP gives you just 2 new commands. To get data, you name the process you're listening to, add a question mark, and then the variable where you want to store the info. To send data, you name your destination, use an exclamation mark, and then say what you want to send. That's it. So clean.
Now here is where the real genius kicks in. The communication is synchronized. The paper is super clear about this. There's no automatic buffering. What that means is, if process A wants to send a message to B, it has to literally stop and wait until B is ready to receive it. And B has to wait until A is ready to send. They have to meet at this digital rendezvous point, do the exchange, and only then can they both move on. It's a perfect synchronous handshake.
And this whole elegant system, it all hangs on one golden rule. Processes have to be disjoint. In plain English, that just means no process is ever allowed to mess with another process's internal stuff. As the paper puts it, a process can't even mention any variable which occurs as a target variable in any other process. This one simple rule is what kills all the chaos from the old way of doing things.
So these simple rules, they're like programming Lego bricks. Let's take a look at how they can be used to build some really complex and, more importantly, reliable systems. Hoare gives us this beautifully simple example right in the paper to show how it all works. A little process whose entire job is just to copy characters from one place to another. It's basically a one-character buffer. All right, let's break this down real quick. We're defining a process, let's call it X. That little star with the brackets just means do this forever, on a loop. So what does it do? First, it waits to get a character from some process called West. As soon as it gets it, it immediately turns around and sends that same character over to a process named East. That's its whole life, a perfect, tiny, self-contained machine. And right here, this is where the magic really happens. You can take these simple, perfectly behaved little processes and then compose them to run in parallel using those 2 little bars. It's just like snapping Lego bricks together. You take these independent little pieces and build massive, sophisticated systems out of them. And this is a great way to visualize that whole idea. A really complex system just becomes a network of simple, independent nodes. And each node only ever talks to its immediate neighbors. All that complexity is managed because you're just putting together simple parts that communicate over these really clear, well-defined channels.
So this was obviously a brilliant idea for 1978. But why are we still talking about a nearly 50-year-old paper today? What's the big deal?
Well, it's because the ideas Hoare published way back in 1978 were so incredibly far ahead of their time. He basically laid a foundation that modern programming is still building on right now.
I mean, seriously, its fingerprints are everywhere. If you've ever used the Go programming language, its channels and Go routines are a direct descendant of CSP. The whole actor model, which is famous in languages like Erlang and Elixir, shares that exact same philosophy. And these ideas are absolutely foundational for building today's huge microservice architectures, where you have all these independent services that have to talk to each other reliably.
And that's really the heart of it. The true genius of Hoare's paper wasn't just some new syntax. It was this incredibly deep insight into how you manage complexity. It teaches us that the best way to build strong, understandable software isn't by adding more bells and whistles, but by putting simple, powerful limits on how the pieces can talk to each other.
As our systems just get bigger and more distributed, that core lesson, well, it feels more important today than it ever has. It's definitely something worth thinking about the next time you sit down to write a line of code.